Alright gang, here we go. So this is Chem 2 Unit 4. We're talking about precipitation reactions. We're talking about how to write molecular, ionic, or complete ionic and net ionic equations. Alright, so here we go. So precipitation reactions, essentially, we've talked about these several times, but essentially what you're doing is you're starting with two solutions that have soluble components in them, soluble solutes, and then mixing them together, and then they'll form some sort of insoluble salt, and that solid that it makes is called a precipitate. So in this example, they're starting with one solution that's got potassium iodide up here. This guy's got potassium iodide, and down here we've got lead nitrate. Okay, and so both of these are clear solutions, soluble ions in there. And then they get mixed, and the potassiums and the iodines, or the lead and the iodines, get attached to one another, and they form a precipitate, which is this yellow stuff here. And so here's our balanced chemical equation. We got iodine with lead nitrate makes potassium nitrate and lead iodide. All right. So, so if we want to predict whether a precipitate forms when strong electrolytes are mixed, we got to figure out the ions that are present, and then in the reactants, and then figure out if whether or not what they'll make is what they make. Okay, and then we use the solubility rules that we looked at last time to figure out whether or not they make a solid. Okay, so for example, here we've got magnesium nitrates and sodium hydroxide. So this is just a double replacement reaction, right, or a metathesis reaction. So you got magnesium, it goes with the hydroxide, you get MgOH2, and then you got sodium going with the nitrate, and you put those two together, and then you just have to look at the anions for each of them on your solubility chart, and you see that, well, hydroxide is always soluble, or is always insoluble unless it's with alkali metals, calcium, strontium, and barium, and that's it. So magnesium hydroxide is actually solid, so therefore this guy is a precipitate. All right, and then so you put this guy in an S. You might also see some people drawing like a down arrow here to show that it like falls out of solution. All right, and then you got sodium nitrate. All nitrates are soluble, so therefore that guy's aqueous. All right. So anyway, so we get these exchange reactions, and they're called metathesis reactions. Pretty fancy word, metathesis, and it means to transpose. Okay, and so you get these guys, and they essentially, it just looks like they flip spots, but we all know that that's not quite what happens, right? So in order to balance a chemical equation, they kind of show you, here's some steps here, but let's just do one together. Here in a minute or two. Okay, so pause the video, read these steps, all right? And then we have to take those metathesis reactions, and there's three different types of reactions we're going to talk about how to write. Molecular equations, complete ionic, and net ionic equations. All right, molecular equations is essentially what we just looked at, is the metathesis reaction, double replacement reaction, just like you're used to. And you're just kind of not caring whether or not their ions are not in solution, and you're just going to write them all out. So you've got your lead nitrate, your potassium chloride, your lead chloride, and your potassium nitrate. And you just put their states and balance it, and Bob's your uncle. So it's a molecular equation. It's showing like the molecular representation of each of these different things that are being involved in your reaction here. All right, so this tells us, what's there, but it doesn't really give us a good idea of what's going on in solution. So the complete ionic equation shows a complete picture of the ions and the solids and anything else that's in their solution. So this is the exact same reaction as we had before, but now we've taken these molecules and we've split them up into their individual ions. So before we had lead nitrate, right? Here's our lead nitrate, and it got turned into Pb2 plus and 2NO3 minus. Okay, so this is the first guy there, right? And then the next one here is we had potassium iodide, potassium iodide, and that's this guy right here, potassium iodide. Whoops, I went the wrong way, wrong arrow. But it's like, that's not right at all. So anyway, so here's our potassium chloride that we came from right there, potassium. They changed reactions on me? No, they just... Yeah, they did change reactions on me. Why would they do that? Alright, whatever, it doesn't matter. Okay. Alright, so they get iodine. Oh my gosh, that really bothers me. Why would they do that? So anyway, so you get these guys, and so this is the pairing that they came up with: lead nitrate and potassium iodine together, and then you get lead iodide. Now this guy is a solid, right? It forms a precipitate, so it's not as ions inside solution. It's just as a chunky solid in there. And then you got these guys, and these are their individual ions. So this is the complete ionic equation. So it shows every single ion that's there in solution, no matter what it's doing, and then if it's anything but aqueous or if it's anything but solid, you go ahead and write it together like it is in the molecular equation. So essentially all you do is, if you can get your molecular equation, then anything that's aqueous, you split it up into its ions. All right. So here's your net ionic equation. So you take your complete ionic equation, and anything that's on both sides get canceled out. So you're canceling out what are called spectator ions. Okay, spectator ions are the ions that are on both sides. So you imagine like this reaction is like a football game. The spectators are the ions that are in the crowds not participating in the game. They might cheer and say "roo-rah" or whatever for their teams, but they're not actually doing anything. So in this case, if we looked at this reaction, notice that the lead here, we got a Pb2 plus on the reactant side, but there's no Pb2 plus on the product side. Now the nitrates, we've got a 2NO3 minus here and a 10NO3 minus here. That tells us that he's a spectator. He's not participating in the reaction. So he's not going to be written in our net ionic. And then here we've got a potassium, and then we've got a potassium over here. So once again, this guy's a spectator, so he doesn't get written in our equation. So what's left is the lead and the iodine and the lead iodide. Okay. And so we end up with this guy as our net ionic equation. All right. So essentially, there's our steps for writing the net ionic equation. One note that they have here in bold is that we only write strong electrolytes in their ionic form. So if you have a weak acid or a non-electrolyte, you don't write them into their ionic forms. All right. And that's it. So here we go. So let's do a couple practice problems. So will a precipitate form from these solutions? So what two products are we going to get? We're going to get barium hydroxide, so that'd be BaOH2, and then we'll also get potassium nitrate, KNO3. Okay, so we're just predicting whether or not a precipitative form. It doesn't really matter if we can write our chemical equation. So KNO3, well, NO3s are always soluble, so no, he's not going to form a precipitate. For barium, I'm pretty sure barium hydroxide is one of the exceptions, so he is soluble. So barium hydroxide will not form a precipitate. So no, you will not get a precipitate if you mix those guys together. All right. What compounds precipitate when aqueous iron sulfate and lithium hydroxide are mixed? Write a balanced equation. So let's go ahead and write the balanced equation first. So we got Fe2SO4 plus lithium hydroxide. All right, and these guys are going to be aqueous, all right, because it says they're aqueous solutions. All right, and then we're going to do a metathesis reaction, or a double replacement. So it becomes iron hydroxide, so Fe. Now this iron had to have a 3+ charge, right, because the 3's down there, it goes up top. So this would be, and OH has a 1 minus, so this would be FeOH3. And then the other side would be lithium sulfate, Li, and then sulfate. Sulfite has a 2- charge. Lithium is an alkali metal, so that means we'll need 2 lithiums for each sulfate. Now we need to decide what our states are going to be for our products. So we find hydroxide. It says hydroxides are always soluble unless they're with alkali metals, calcium, barium, strontium, or ammonium. Iron is not one of those 3 things, so therefore iron hydroxide is a solid. All right, and then we get lithium sulfate on the other end. We find sulfate, and it's always soluble unless it's with silver, calcium, strontium, barium, or lead. Well, lithium's none of those things, so therefore it's going to be aqueous. Now we get to balance it. All right, so essentially our answer to A is going to be the FeOH3, right? So that's the answer to A. Now we have to balance this thing. So we got Fe2, so we put a 2 here. All right, sulfate SO4, so 3. So we'll put a 3 there, and then lithium hydroxide. So there's lithium. There's 6 lithiums here, so we'll put a 6, and then hydroxide 6, 6. All right. Well, that was nice. So we got that as our balanced chemical equation. All right. let's skip this one and we'll do the second one here. All right, it says write the net ionic equation for the precipitation reactions that occurs when aqueous solutions of silver nitrate and potassium phosphate are mixed. So this is a full-on let's go get 'em kind of thing. All right, so silver nitrate, AgNO3, and remember silver we always assume is 1+ unless it says otherwise, and it says aqueous, so we'll put an aqueous right there, and then it's reacting with potassium phosphate, so that's KPO4. Now, and this guy's also aqueous. So phosphate has a charge of 3-, potassium has a charge of 1+. So we need a 3 here for our potassium, K3PO4. All right, we put our arrow, and now we do our double replacement reaction. So we get silver phosphate. Ag has a charge of 3. Phosphate's got a charge of 3-, so we'll put a 3 down there. Silver's got a charge of 1, Phosphate has a charge of 3-, so we put Ag3PO4, and we don't know the state yet, so we'll put that there like that, and we'll put a plus sign. And the other side of it is a KNO3, and we should know by now nitrate always is soluble, so that's aqueous. And then phosphate, so we find phosphate here. Phosphate is always insoluble unless it's with a group 1 metal or ammonium. Silver is neither of those things, so therefore that guy's solid. All right, now we got to balance it. So we've got 1 silver here, 3 silvers here, so we'll put a 3 right there. 1 nitrate, 1 nitrate, 3 potassiums. Oh, I'm sorry, we've got 3 nitrates, 3 nitrates here, right? Because we put that 3 nitrate. So we need a 3 here. And then we've got 3 potassiums, 1 phosphate, 1 phosphate. So we're balanced. All right, so this guy here is our molecular formula. All right, we'll just label that. Now we're going to turn this into our complete ionic. All right, so now we're going to rewrite these guys. Everything that's aqueous is going to turn into ions. All right, so this guy's aqueous. Yep, aqueous. So silver, AgNO3. So it turns into, we get 3 Ag pluses, right? And this is aqueous. And then we get 3 NO3 minuses, aqueous. All right, so that's what this guy turns into. And then the potassium phosphate, well, that turns into 3 K pluses, aqueous, and 1 phosphate, so PO4, 3- aqueous. All right, so those are all of our reactants. All right, so we get those 4 ions are what are participating in reaction there. And then this guy turns into, well, this is our solid, so it doesn't get touched. Ag3PO4 solid, just like that. And then the other half of it, we get 3K plus aqueous, all right, plus our nitrate, which is 3NO3 minus aqueous. All right, so that is our complete ionic equation. So this is our complete ionic, all right, equation, complete ionic equation. But it asked for the net ionic equation, so we have to go through and cancel out all of our spectator ions. So we have silver plus on this end. We don't have any silver plus ions on this end, so it doesn't get canceled. Nitrates right here, there's an NO3 over there, so that gets canceled. All right, so those guys are spectators. You know, play or get out of the way kind of thing. And then we get potassium, 3 potassium, 3 potassium. So those guys are spectators. And then phosphates turn into that. So therefore, we're going to write out our equation with just these guys that didn't get canceled. So it becomes 3Ag plus aqueous plus PO4, 3 minus aqueous goes to Ag3 PO4 solid. So that is our net ionic equation. Wasn't that a lot of fun? So this is going to be kind of involved. So anyway, do lots and lots of practice problems. It's kind of a culmination of lots of things we've been talking about: polyatomics, charges, nomenclature, you know, solubility rules. You know, there's a lot of things to know how to do in order to get just one answer. So anyway, do lots and lots of practice problems. Let me know if you have any questions. Next thing up was acids. Should be lots of fun.